modern way to represent this kind of architecture is by using only small boxes that represent the transformation done on the data. So instead of representing processing unit with circles and connection, you can see that it can take a lot of time to draw this architecture, even if it's more beautiful than only this simple series of boxes. Because of the complexity of the architecture we are developing, we will just say we give a vector of n numbers, and we know how this vector have been generated by the data, because we know the pre-processing done on the data. Then this vector will be given to a module called the dense, which is really a linear transformation. The dense are the connections here, the multiplication of the parameters with the value associated to the processing units. Then we use an activation. So this module concerns the operation on the hidden neurons. Then we have another dense, which is associated to these connections, activation, dense, activation, and we obtain a vector as an output. So we are representing the same thing, but in a much simplified way. And the name of these modules are important because now the libraries that you are using, TensorFlow and PyTorch, they standardize the name of the operation that before was represented that were not defined with any name. It was just given by this kind of architecture. So let's see the dense module. So it's a vector-vector multiplication. This little diagram, I will decompose it as this operation, and we'll see that with a module, I can also do operations more efficiently. So how can I implement the dense module? So I will use one row vector for one example. Here I have only 4 features, like the iris. Then the connection, I will have 4 connections. It will represent my pattern. I do the dot product. I will multiply component by component and then sum. And I will have one scalar that will be the representation, the next representation, which represents if the pattern has been found in the example. If I have multiple patterns, I can stack the patterns over the columns. So now I have a matrix. This is a 1x4 vector. This is a 4x3 matrix. If I multiply both, I will obtain a 1x3 vector for my representation. So now I'm doing only matrix vector multiplication. And I'm representing the operation done here. And since I still have 1 degrees of freedom to do linear algebra, I can add some examples here to go from a vector to a matrix. So here I have 2 examples that I have stacked. It's a 2x4 matrix times a 4x3 matrix. It will give me a 2x3 matrix. And because I'm doing a matrix-matrix multiplication, we know that linear algebra libraries, which implement like the BLAS API, are very, very effective. They are super effective to perform this kind of computation. And on GPU, it's even faster. And dense module will be used everywhere in our architecture. So that's why we're using GPU. We implemented this simple step in the artificial neural network as matrix-matrix multiplication. So the advantage over classical diagram, data and patterns are now stuck in tensors. So we are using vector, matrix, or ND arrays. Now the deep learning operation will be encapsulated in modules. So we will see different modules during the school, but really in the libraries you can just take one module, use it in your architecture, and link the output of one module to the input of another module. And so you will create this architecture only by using modules where all the complexity of the operation have been encapsulated and have been programmed for you very efficiently. Also, the modules can process multiple examples in parallel. This is super important to train the model efficiently. It's implemented with linear algebra on GPU. And we will use this modular approach to define architectures. If you are communicating your work to someone else, you can just say, I'm using the VGG model. And VGG is pretty standard. It has thousands of citations. It's a paper which presents a new architecture, and it works very well on different tasks in vision. And people knows what is VGG in the community. It's really a very famous model. But inside VGG, there are a lot of convolution with match spooling, different operations that themselves are composed of other operations. And you can see that everything is encapsulated here. But also, these modules can encapsulate complexity until you go to the single addition, multiplication, and dot product. At the bottom of this hierarchy, you will have the elementary operation. Also, the activation function can be encapsulated in modules. So here I was using these yellow dots to represent that this module have parameters, but the activation function doesn't have any parameters. The parameters of the dense module are the values over the weights, over the connection. But an activation function doesn't have any parameters. So a module is an elementary building block that we can combine with others to create new modules. And this is something that is very effective because now I can create the inception module, which is not the whole inception architecture. It's only a sub-part of it. And maybe this module can be interesting to capture some features and create interesting representation. And this inception module can be used by other architecture. And I have also the inception model, which is much more complex, but can be encapsulated into a single modules too. So here's an example. This is the inception model. And here they are not using much encapsulation. Each little byte is elementary operation. And the data will come in here. And you can see how the data are processed until the output of the model. So we have one output here, one output here, and another here. So it's super complex, but as an exercise, you can try to find patterns in this architecture and define a module that will encapsulate some complexity and link these modules together. And it's an interesting exercise because you don't want to program in one function all these tiny modules. You want to create a class that will be a sub-module, and you want to reuse these sub-modules again and again to reduce the length of your code. So another question is, how can we build a probabilistic model with these complex architecture? When I say I want to recognize if there's a cat or not in the image, really what I want to predict is the probability of a cat, because it's much more flexible. Instead of saying only cat or no cat, my model can say, I'm 90% sure it's a cat. It gives us much more information, especially if you are doing active learning. If the model is saying 50% of a cat for an unlabeled data point, you can ask to the annotator to give the label because the model is uncertain. So how can we create a probability? So for binary classification, it's really easy. I can use any model as complex as I want that will pre-process the data. And at the end, I just add one single module, which is the sigmoid module. And the sigmoid will return a value between 0 and 1. And this value will represent the probability P of is there a cat or not in the image. It will be the parameter of my Bernoulli distribution. So P is the probability of class 1, and 1 minus P is the probability of class 0. So I just converted my very complex architecture into a probabilistic model by adding a sigmoid. If I want to do multi-label classification, remember we had this image where we want to find all the objects in the image. So here I have in my dictionary 6 concepts: cat, car, person, tree, dog, and bike. And for each of the concepts, my model must predict, is the object in the image or not? And the prediction is done concept by concept. So here the model is pretty certain that there are persons in the image. There is no cat in this image. And the model is 60% sure that there is a bike in this image. So how can I model it? I can use again the sigmoid module. But now in this module, I must take the last representation, and I must use a dense module to convert a representation of an arbitrary size to the number of concepts that I want to predict. So if I have a vector of 800 as a representation, I use the dense to convert 800 to 6, and then I use a sigmoid function over my vector of 6 to have one probability per component of the vector. And so for multi-class prediction, now I must identify one and only one concept in the image. So it must be a cat, or a dog, or a horse, or a tiger, or a penguin, but it cannot be 2 concepts at the time. It's only one among the n concept. Here my model is sure at 90% that it's a cat, but also it may be a tiger with 8% and a dog with 2%. What we want to achieve here is that each number is between 0 and 1, and also that the sum is 1. So here I have 90 plus 8 plus 2. I will have 100% prediction over all the object. It represents that the object that is in the image must be one of these concepts here. It cannot be any other thing. If you want, you can also add another component here to say other, and maybe the model can use other when the concept in the image is not in the dictionary. So how can we model this probability in multi-class? We will use the softmax module. So the softmax is defined here. So for the vector of size n, the probability associated to one component will be the exponential of this component, and I will divide by the sum of the exponential over all the components. So it's called the softmax module.